Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Bruce Partridge, who is an Emeritus Professor of Astronomy at Haverford College. He has served as Education Officer of the American Astronomical Society, President of Commission on Cosmology, International Astronomical Union, and President, Astronomical Society of the Pacific. His research interests include cosmology, galaxy formation, the cosmic microwave background, and radio astronomy. Welcome, Bruce.
Thank you.
I want to start with the Planck satellite. There was an overview, a study entitled Overview and the Cosmological Legacy of Planck. The Planck satellite, European Space Agency, sent that out in 2009, I believe, and collected data for about 4-year period that substantially changed. Well, it didn't change our understanding, but substantially confirmed much of our understanding through the data.
I think that's the right way to look at it. Planck was designed to map the cosmic microwave background, the heat left over from the Big Bang.
Yeah.
That surrounds us in a surface called the surface of last scattering. Small changes in intensity on that surface can be mapped, and they tell us about the origin of structure in the universe.
Right.
So
the CMB is really a look at something like 380,000 years after Big Bang or something like that.
Exactly. So we're looking back. They're essentially, as I like to say, baby pictures of the universe. But imprinted in those baby pictures is a lot of information about the structure in the universe, the composition of the universe, both ordinary matter, and dark energy. And Planck was designed to do this map over the whole sky to the limits set by astronomical foregrounds and what's called cosmic variance, and that it did.
So
yes, go ahead.
So from a design perspective, Bruce, so this is really just measuring microwaves. Is that the sensors on Planck?
The reason for selecting a certain frequency band is that the temperature of the microwave background at about 3 Kelvin peaks up in terms of its intensity at the wavelength of a few millimeters. In addition, you want to operate at frequencies where foregrounds, like emission from our own galaxy, don't swamp the signal you're interested in. So we operated with a range of frequencies, 9 different frequencies that spanned the sort of sweet spot for detecting the CMB, the microwave background, against the foregrounds of the galaxy.
Okay, so these frequencies, you say this is in the range of 330 to 800 or so gigahertz?
From about 30 to above 800 gigahertz, yes. And the sweet spot, as I keep mentioning, is around 50 to perhaps 150 gigahertz. We did lower frequency and higher frequency measurements to monitor the foregrounds and get rid of them in the cosmic signal.
So, so we are interested mostly in the 50 gigahertz range. So what's the reason to prefer that frequency?
Essentially, at lower frequencies, there's radio emission from our galaxy that's much stronger than the microwave background. At higher frequencies, there's emission from dust in our galaxy that again swamps the microwave background. So you have to work in the middle, in this, as I say, the sweet spot, to avoid being swamped by one or another of these foreground signals. So that's why we emphasize the middle, but we also measure the extremes in order to get rid of or mitigate the galactic signals.
Okay, so it's a bit like, I don't know much about this, Bruce. I'm just speculating. So it's a bit like you take multiple pictures and sort of superimpose them so that you can remove the noise in some way to get to the pure CMB.
That's close to being right, yes. Imagine if we talk about ordinary light, taking a picture in the red where you're swamped by the red light of the sun, taking a picture in the blue where you might be swamped by reflections from the ocean, and using those measurements, subtracting the signals you get to leave you a good view in between, at in between wavelengths or frequencies. So it was simply a way of controlling the foregrounds.
Right. And so Planck is going to provide a large amount of data, and then I guess you need to post-process that data to make sense out of it.
Indeed. I mean, Planck stopped operating 7 years ago, and we're still analyzing the data. It's a huge data bank, and we have several problems. One is dealing with the foregrounds, using the high frequency and measurements to improve the middle frequency measurements where the cosmic information is. And the other is that, like any experiment, Planck had a series of systematic problems or uncertainties that we needed to address. So we're poking away at it. And even though the Planck collaboration itself has now stopped, other groups are working to go beyond Planck in terms of analyzing the data and extracting cosmological information from it. It's a very rich data legacy.
Yeah, so the duration of this, Bruce, 2009 to 2013, appears somewhat shorter, right? But why is it only 4 years?
Two answers. First, Planck, unlike some earlier satellites, was cooled. And some of the detectors, particularly at high frequency, operated only with the coolant, and that ran out after roughly 2.5 years. But we were able to keep other refrigerators going for the lower frequency detectors. Okay. So we kept going for roughly 4.5 years. Then it was a question of money.
Right. Okay.
To be frank.
So this is not a problem we face in the typical sort of visual, what's the right term, when we make a measurement of the light that we can see. The cooling issue is because of the microwave at this sort of frequency. That's the issue.
Yes, you need to cool the detectors to very low temperatures. In the case of the high frequencies detectors, for instance, we use 3 refrigerators to reach temperature of the order of 1/10 of a Kelvin. And that's necessary to reduce the noise. Think for a moment about what we're trying to do. We were looking for changes in temperature out there on the sky of the order of a few microkelvin, with an instrument itself that was sitting at a temperature of about 50 Kelvin in space, and detectors that were at 100 millikelvin. So we had to use all kinds of tricks to reduce noise coming from relatively hot surfaces like the instrument or the detectors to get at these very faint fluctuation signals.
So the
Need for
instrument
cooling.
itself, so instrument itself is at 50 Kelvin. I guess the average temperature of the CMP is around 3 Kelvin.
Yes.
But the fluctuations is in the order of microkelvin. So that's what you're really trying to capture.
The fluctuations that I've been referring to in the temperature are typically bigger than that, of the order, roughly speaking, of 100 microkelvin. But we needed to detect them with high sensitivity. So we aimed at sensitivities of the order of a microkelvin in each little part of the sky.
And so the trick was, from a design perspective, to keep the satellite at 50 Kelvin. And so once it's above that, it sort of runs out of its utility.
Yeah. Keeping the satellite at 50 Kelvin itself was not easy. We needed to shield it from the light of the sun very extensively. But the optical surfaces that first intercepted this light coming from the Big Bang, they were cooled to a temperature of roughly 50 Kelvin. And then refrigerators started at that temperature and reduced it in several steps down to 4 Kelvin and eventually 0.1 Kelvin.
Is the satellite still up there?
That's about 494 degrees below 0 Fahrenheit.
Right. Yeah. Is the satellite still up there, Bruce?
As far as we know, yes.
And so
it was in
yeah. Go ahead.
We don't really know.
Right.
It's floating around. It's in not so much an orbit as a sort of position, designed in such a way that from the satellite to the Earth to the sun was a straight line, so that the satellite could always face away from both the Earth and the sun, called the L2 point.
Yeah.
And we assume that it's left that position, but we don't, as far as I know, we don't know where it is.
Yeah, I mean, I was just wondering, given that it was only a 4-year mission, whether there was an opportunity to have an instrument that does not need such a low temperature. I wondered if something else could be combined with it, or that wasn't possible.
Well, it was launched along with another instrument, but it operated on its own. You have to be careful because the optical elements, the telescope, as it were, that we used was pretty big. So there wasn't a lot of room on our little satellite for other things to go along. But when it was launched by ESA in 2009, it went up with another instrument.
Okay. And so from a technical perspective, light that escaped 380,000 years after the Big Bang got redshifted all the way to the microwave region. That's what we're trying to measure.
That's right.
And we got really good data, right? Planck really made a huge difference in terms of confirming what was expected from a technical perspective, I gather.
From a technical perspective, yes. Our aim was to make a measurement that could not be improved, because the measurement is limited not by instrument problems or sensitivity, but by nature. And we did that. So we've measured these little fluctuations as well as they can be measured up to a certain angular scale. If we're interested in really tiny angular scales, ground-based instruments can do better. But from angular scales of hundreds of degrees down to several arc minutes on the sky, Planck has done the definitive measurement. Can't be improved. And that's what we said we would do. That's what we did.
So when we see the CMB, sorry, Prof.
No, go ahead.
No. So when we see that CMB picture, are we seeing just a short window? We're not seeing the whole thing.
When you see the standard map, it's a sort of oval, and that oval represents the entire sky, sort of rolled out onto a two-dimensional surface. So you're seeing the entire sky, typically with a band running through the middle, which is the plane of our galaxy. What you're seeing is first false color. The sky is not the colors that you see. We're just using red or blue to indicate higher or lower temperatures on the sky.
Yeah.
The other thing is that you're seeing a single surface at a single time. The image I like to use is the following. Suppose you look out on a clear day that happens to have a big cumulus cloud floating around. What do you see when you see the cumulus cloud? You don't see anything between you and the cloud. You don't see anything inside the cloud. What you see is the surface. And the reason for that is that light from the sun bounces around inside the cloud until it reaches the surface. And then it stops scattering and bouncing around on little water droplets and is free to travel from the edge of the cloud to your eye. Same thing is true for Planck. In the early universe, light was bouncing around, scattering not off water droplets, but off electrons. 380,000 years after the Big Bang, the electrons suddenly went away, and then the light is free. It's no longer scattering. It's free to travel in straight lines to our telescope.
Electrons essentially made hydrogen atoms at that point, right?
Yes. Why the electrons went away is that the universe 380,000 years after the Big Bang was cool enough for hydrogen atoms to form. And oddly enough, hydrogen atoms contain an electron, but that electron does not strongly scatter radiation, whereas free electrons do. So it's scattering and sudden cessation of scattering.
Right. So it's almost like it was opaque prior to that, and then it became clear and the photons escaped, I guess.
That's right. Exactly like a cumulus cloud. You can't see into it because it's opaque. You only see the surface. And that's really helpful because we know when that moment occurred with quite high precision. So we have a measurement of the properties of the universe at a known time.
Yeah. And how long would that process have taken? In other words, it's opaque at one moment and it's clear on another. How long would the duration be between those?
The duration would be of the order of 5% of the total, or less.
Okay.
So I'm trying to do this quickly. 5% of 380,000, of the order of tens of thousands of years.
Okay.
But it's quite, in cosmic time, it's quite sharp. And that's true of the cumulus cloud. It's not a absolutely firm, hard surface. It's a little fuzzy. And the same is true of this surface of last scattering when the free electrons go away.
The article says, Bruce, Planck measures 5 of the 6 parameters to better than 1% simultaneously.
Yes.
And the best determined parameter, theta, now known to be 0.03%. So what are the 6 parameters that Planck set out to measure?
Okay, before I list them, how extraordinary it is that we can describe the entire evolution of the universe from the first few seconds up to the present time with just 6 numbers. It's really quite remarkable.
Yeah.
Parenthetically, we've looked to see if you can get a better description, better fit to the data if you add a 7th, an 8th, a 9th. And the answer is no. 6 is fine. Okay. So what are they? Some of them are very easy. The amount of ordinary matter, what's called baryonic matter, the stuff that makes up people, planets, stars, and so on, consisting mostly of neutrons and protons. Dark matter, this mysterious thing that we know exists but don't know exactly what it is. And dark energy.
Yeah.
Then there's a slightly more complicated number, as it were, that has to do with the scale, in angular scale, of the fluctuations. And that in turn is linked to the Hubble constant, which is a measure of how fast the universe is expanding. So I'll cheat a little bit and say what the universe is made of, how fast it is expanding, how the amplitude, now not how big they are, but how dense or rare or high temperature, low temperature these fluctuations are, how that number depends on angular scale is another of the parameters. I think we're up to 5, incidentally, all well measured by Planck. And then the last one is interesting. Go back to this analogy with the cumulus cloud. I said the light leaves a cloud and then it travels in straight lines to your eye. The microwave photons leave the surface of last scattering 380,000 years after the Big Bang. They travel freely towards you. But because at some later time, probably of the order of hundreds of millions of years after the Big Bang, stars broke apart the hydrogen atoms into protons and free electrons. So there was a little bit of additional later scattering during a period which we call reionization. Hydrogen was reionized, free electrons were reintroduced. That's really hard to measure. Planck did a very good job of it, but it's not at the 1% level. It's at the 10% level.
Right. And so if I understand this correctly, Bruce, so the amount of ordinary matter, dark matter, and dark energy, so it's sort of the composition of those 3 things, right? Approximately 5%, 25%, and 70%. So Planck confirmed that sort of a breakup of those 3 things?
Yes. And it did it in an interesting way, in a sense. The measurements of Planck and some earlier measurements indicated that you had to have dark matter. You could not make a universe that just had ordinary matter, even if you added dark energy. You had to have dark matter. Planck really pinned down how much dark matter is needed. And then Planck also made an independent measurement of the amount of ordinary matter. And that's interesting because there's an entirely separate way of determining how much ordinary matter there is in the universe. And that goes back to the first 3 minutes, not years, minutes of the history of the universe. Remember that there were protons and electrons floating around at these early times because the material was ionized. There were also some neutrons, and how many of them get trapped into the nuclei of helium atoms depends on the amount of baryonic matter there is, how many neutrons, how many protons there are in each cubic meter of the universe at these early times. So by looking at the amount of helium that came out, we can project back to the first 3 minutes and say that the amount of density had to be such and such, about 5% of the total, And that's exactly what Planck is finding. So making a measurement now of the universe when it was 380,000 years old agrees with an entirely different measurement made now of what the universe was like 3 minutes after it was founded. And they agree. And parenthetically, they agree because general relativity works. So Planck is also a means of testing the validity of general relativity over big stretches of time.
That's amazing. So this 52570 break though is sort of the status quo measurement, right? So if you rewind time back, those things would be different,
Absolutely.
right?
In the following sense, as the universe expands, both ordinary matter and dark matter grow less dense just by conservation of mass. You expand the volume, same amount of stuff in a bigger volume, the density drops.
Yeah.
But that's not true of dark energy. Dark energy has this truly bizarre property that its density stays constant. So if you double the volume, you don't have the density. You simply double the amount of dark energy. So dark energy now is not going down in density, but the other two ingredients are going down in density. So come back in, let's say, 100 billion years, the density of ordinary matter will be a lot less. The density of dark matter will be a lot less. The density of dark energy will be exactly the same as it is now.
And that break between the three will get more and more dominated by dark energy, right? If we just go forward in time, at some point, it will be almost 99%, 99.99%
Yes, if you
dark
go
energy.
forward enough in time, dark energy wins. But interestingly, if you go
Right.
back in time, the opposite is true. So if you go back to redshifts of order 1, let's say several billion years into the past, then the dark energy was not dominant in the way it is today. There was a period where the density of dark matter fell below the density of dark energy in the distant past.
So the dark energy sort of has a runaway expansion effect on the universe, and in some sense, that's what happened during inflation too,
Yeah.
right? But at that point, dark energy wasn't dominant, so it was something entirely
It had to be something entirely different. Yes. One of the great mysteries of dark energy is that it's so incredibly weak compared to whatever it was that was producing inflation in the first 10 to the minus 30 seconds of the history of the universe. They're somehow disconnected phenomena, or we don't understand the connection between them. So the universe started out in a state of inflationary exponential expansion, settled down to being dominated either by light or matter, and now is in a phase where it's the dark energy that's again dominant.
Yeah, it is. But Planck made such a big contribution to the field. What has happened since Planck? So what is the post-Planck instrument that we are banking on?
Oh, let me answer in a number of ways. First, post-Planck, part of it is extracting from the data we already have new and interesting things. Let me give you an example. Planck looks at these fluctuations, changes in temperature on this surface a long way away. But that light is traveling towards us, and as it does, it passes by other chunks of matter, which gravitationally deflect the path of the light a little bit. It's called gravitational lensing. So by using the background light from the microwave background, we can measure where all the mass is in the universe. And Planck has published maps of the mass distribution in the universe. That's now being refined by a bunch of young theorists. So we're using the data we've already got to learn new things.
Yeah, and it could go on for a little while because you got tremendous
exactly.
amount of data.
In addition, there's a very active program of ground-based experiments which are designed primarily to look at these same fluctuations, the same surface at 380,000 years, but in much finer detail. It's sort of like the difference between looking at the moon with your eye and looking at the moon with binoculars. You can see a lot finer detail. And it turns out there's an awful lot of physics involved in the small scale fluctuations. An example that comes out of this merger of small scale observations with Planck is that currently the microwave background provides us the best measurement we have of the mass of a subatomic particle called the neutrino. You'd think that would be measured in a laboratory at CERN or someplace like that, but the best measurements come from the microwave background because the mass of neutrinos affects the fluctuations we see. So there's all kinds of use of current data, lots of ground-based experiments going on, and plans for an additional space experiment. The only one that's up and running at the moment is a Japanese satellite called Lite Bird, L-I-T-E Bird, that's designed in a sense to repeat Planck's measurement, but to concentrate on big angular scales and polarization. I haven't talked about that yet, but polarization is important. And interestingly, it is going to operate with 14 or 15 different frequencies. Again, low frequencies to control emission from our galaxies, high frequencies to control a different kind of emission from our galaxies, and then a bunch of frequencies in the sweet spot. That's scheduled for launch late in this decade. So there's a lot still going, and plans for additional satellite and ground-based experiments are ongoing as well.
Right. We'll take a quick break, Bruce. So when we come back, we can talk about that. We can talk about ACT, ALMA, and you mentioned polarization, perhaps BICEP.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So, Bruce, we are back. We are talking about the Planck satellite that ceased operations in 2013, but in 4 years from 2009 to 2013, collected a tremendous amount of data and confirmed much of what theoreticians have been sort of laying down, but experimentally sort of confirm much of that. And the data is still being analyzed post-process, so to speak, to get more and more insights from it. But to complement that, we have now ground-based instruments, and one of them is ALMA, right? So ALMA is Atacama Large Millimeter Submillimeter Array. So this is in Chile?
It's in Chile, but it is not particularly well suited to do these microwave background observations. Instead, most of the ground-based work, both in Chile and at the South Pole, are somewhat smaller telescopes specifically designed to look at the microwave background. In a sense, ALMA has too high resolution. It's a huge array of telescopes, and it's designed to look at small patches of the sky with incredible resolution.
And so
And
you
the
say in this
idea for
paper,
yeah,
this is a recent paper, Bruce, you say confirming the calibration of ALMA using Planck observation. So you're basically sort of
ah,
testing whether ALMA data is consistent with what we saw with Planck.
exactly right. This is work that I'm doing with a student
Yeah.
named Garrett Farron now at Cambridge. Um, and it's the following. Planck, in addition to looking at the microwave background and doing a good job of that, also detected lots and lots of radio sources. We have of the order of 1,000 or more radio sources in our Planck catalogs. Well, ALMA also observes those radio sources. So we can compare what ALMA sees with what Planck sees. Planck, unlike ALMA, is absolutely calibrated. That is, we know exactly how much energy is entering the Planck telescope from any given object in the sky. And the idea that Farron and I had was to transfer that calibration from Planck to ALMA. It's slightly tricky, but the idea is not to look at things that ALMA can't, but instead to make sure that when ALMA says an object is, to use radio astronomer units, 1.34 Janskis, it really is 1.34 Janskis and not 1.45. And that's what we're working on.
So these radio sources you talk about, Bruce, these are way back in time, like quasars?
Yes, exactly. Most of the bright ones are quasars or things similar to quasars. So we're using them just as a device. We're not particularly interested in the properties of the quasars. We just want to look at a bunch of them so that we can measure how bright each one appears to the two instruments, Planck and ALMA, and compare. It's non-trivial because quasars are often variable. So if Planck and ALMA look at them at different times, they may see different brightnesses. And that's a problem because, as you noted, Planck stopped observing in 2013 and ALMA didn't really start until 2012. So we use a trick to get around that problem.
Yeah, so these quasars, I guess is way back in time, and so are they essentially redshifted all the way to microwave too, or why
No,
does yeah
they emit, in addition to the optical light,
yeah
they emit, many of them, not all, emit strongly in the radio.
okay
So they're plenty bright. We're looking at objects that are typically of the order of 1,000 to 100,000 times brighter than the faintest radio sources. And there are plenty of these bright ones to make this comparative measurement.
okay. Nearby there is another telescope, right? The Atacama Cosmology Telescope, ACT.
Yes, and that one is one of the ones I referred to that's specifically designed for cosmology, not for the study of distant galaxies or distant solar systems like ALMA. It's designed to look at relatively high resolution, small angular scale at the microwave background. And it's now covered about 40% of the sky. And it is pouring out data at a rate that is soon going to exceed Planck if it hasn't already. And that's just one of two. There's another, the South Pole Telescope, which is doing the same kind of thing, but from the South Pole. They're balloon experiments that try to get above as much of the Earth's atmosphere as possible because the atmosphere gets in the way of radio observations. So they're very active programs trying to improve measurements of this special surface that we see at 380,000 years after the Big Bang.
Yeah, the South Pole Telescope, that is not the BICEP, right? It's something different.
Uh, BICEP is, I believe, also at the South Pole. There are various generations of telescopes and instruments at the South Pole. But BICEP has a very specific aim and a very specific design. The South Pole telescope and the ACT Atacama Cosmology telescope are both big instruments, 6 and 10 meters across. BICEP does something very different. It has a small instrument, a small aperture telescope. So it's only looking at the very largest angular scale. So instead of trying to map the whole sky fairly precisely and at high resolution, it maps a small chunk of the sky with big beams, big chunks of the sky each time, but over and over and over again to reduce the noise.
And so I understand that BICEP had a very specific objective, right? So one of the, going back to the CMB, the idea of inflation was proposed. We haven't really confirmed inflation experimentally, right? So there was an idea that we might be able to do that. That is what BICEP was trying to do.
Yes, I mean, there's all kind of evidence that's consistent with early inflation. That is, inflation at around 10 to the minus 30 seconds. Yeah. But the smoking gun, the thing that you most want to see coming out of inflation, is a polarized signal. So let me talk a little bit about polarization. People are familiar with the polarization of ordinary light from polarized eyeglasses. The same kind of phenomenon, light can be polarized on that surface of last scattering at 380,000 years. And it can be polarized in a number of different ways. One particular way, which we call the B-mode polarization, can be produced essentially only by gravitational waves that are set up during the inflationary period. So the link is inflation, gravitational waves, B-mode polarization, and that's what BICEP was looking for.
So what's the mechanism there, Bruce? So the gravitational waves starting during the inflationary phase to make an impression on that surface 380,000 years later, it would require these gravitational waves to be sort of present at that time, right? How does it work?
It would require the gravitational waves to be present, yes, and to pull things around. That's the essential operation. Think again of the analogy I used earlier of scattering in a cumulus cloud.
Yeah.
If the scattering is uniform in all directions equally, the light that comes out is not polarized. But if you can apply or induce a particular direction somehow, then the light can be polarized. And the gravitational wave does that. It applies, in a sense, a direction locally to these fluctuations, and that renders them polarized.
Right.
It's rather tricky and complicated, but the phenomenon or the model is well understood, and we expect to see a particular pattern. It's interesting. It's sort of like a child's pinwheel, those little toys. And around a region of the sky that's a little bit warmer, there's a pinwheel of polarization in one sense. And around parts of the sky that are a little bit colder, the pinwheel goes in the opposite direction. And that's the pattern that BICEP is looking for.
And if it found it, it would confirm the inflation hypothesis. And in some data, we thought we found it, right? What happened there?
Yeah, I would say not if you can if you find it.
Yeah.
If you can find it and show that it's not due to something else,
Right. Okay.
then it's a smoking gun.
Yeah.
And that was the problem with BICEP. They found the pattern. There's a lovely picture in one of the BICEP publications of these little pinwheels, exactly what you'd expect. But it turns out, damn it, that our galaxy can also introduce polarization
Mm.
in light. And if you can't subtract the background light from our galaxy that's interfering with the CMB, then you can get fooled. And that's what happened to BICEP. They didn't have multi-frequency measurements. They couldn't control and understand the emission from our galaxy, so they got fooled.
Mm.
And that's
So that
why Lightbird is going up with
mm.
15 different frequencies. Then I want that to happen again.
So that's a way to sort of correct that problem. So you need multi-frequency simultaneous measurements.
That's right. And you use the high frequency measurements to measure and control for dust emission, low frequency measurements to get rid of radio emission, synchrotron emission from our galaxy. And Lightbird is set up to do that. BICEP wasn't. Planck, incidentally, was, but our detectors were not as sensitive as BICEP. So we had to struggle and struggle hard to search for this B mode polarization, the smoking gun polarization. Interestingly enough, the current best measurement, and it's not a detection, it's an upper limit, but the current best upper limit on the B mode amplitude does derive from Planck data, a recent paper by Mathieu Tristam. So Planck is still churning out results. BICEP surely will too, but we haven't yet detected this particular kind of signal. And that's what Lightbird is trying to do.
Yeah, because Planck has multiple slices at variety of frequencies, that data might ultimately be useful for something like this.
It certainly will. And
Yeah.
indeed, the BICEP team and the Planck team got together a year or so after the first BICEP announcement to do a joint paper using the BICEP data, which is so good on large angular scales and is so good in polarization, and the Planck data, which is so good at detecting dust and getting rid of it. We put them together and produced a joint paper that set what was the industry standard for a while for an upper limit on this B mode polarization, only recently bettered by BICEP and now slightly bettered again by Planck.
And with the Japanese satellite, so you now have three sets of data coming from various sources, various frequencies. Presumably that entire data set should tell us if it is present or not, the polarization, I mean. Yeah.
Well, we hope so. The problem is that we have no theoretical convincing understanding of how big the gravitational wave background should be, how strong it should be. The simplest theories for how strong it should be have already been ruled out by Planck, by BICEP, and earlier experiments. But there are many, many other theories. I like to say that there are 900 theorists working on this problem, and there are 901 models for inflation. We've eliminated, of the 900, we've eliminated, let's say 600, but there's still 300 to go. But the Lightbird satellite, if it's successful, should lower the upper limit by a factor of 20 to 50. So it's a really big improvement if it works.
But there has to be gravitational waves if inflation existed. There's no doubt about that, right?
Yes, almost.
Almost.
You can
Okay.
make a model and This is one of the 901 models. You can make a model in which they're very, very weak, that there are fluctuations in ordinary matter and dark matter, which we see, but the gravity waves, because of the particular properties of the model, are very, very weak. So it may be that some number of models will survive even the Lightbird test. We don't know yet. But if we do see these gravity waves, B modes, then that is, as I keep saying, a smoking gun for inflation. We just haven't got there yet.
Yeah, the complication is that, yeah, so if we do see it, it confirms something. But if we don't see it, it does not rule it out. That's the problem, right?
That's right. That's entirely right. On the other hand, let's remember that there's lots of other observational evidence that supports inflation. So it's not that we don't know anything about inflation. It's very likely true. I'll give you one example.
Yeah.
Why does the universe not have strong spatial curvature? That is, the three-dimensional structure of the universe is very close to ordinary three-dimensional Euclidean geometry. Why is that? Well, one argument is that any curvature that might have existed got inflated away. The universe got so big so fast that the curvature was simply inflated away.
So no, any initial conditions with inflation would have resulted in what we see.
That's right.
Any initial conditions.
Let's go back to a time when the universe, as measured by its age and the speed of light, was, let's say, the size of a soccer ball. Okay?
Yeah. Yeah.
Why wasn't the curvature the same as a soccer ball? Okay, maybe it was. But then inflation increases the scale of the universe by many, many orders of magnitude. So you take a soccer ball and blow it up until it's the size of the solar system. There's not a lot of curvature left.
Right.
And
so, yeah.
Parenthetically, Planck has shown that the curvature is extremely small.
That is still not a confirmation of inflation, right? There could be other possible phenomena that we haven't really put into theory.
Absolutely true. That's why I think I've been careful to say that these observations are consistent with inflation. They don't prove it. That's why this B mode polarization, it would be so interesting to detect, because it's much closer to a proof than just another consistency argument.
Right. I want to touch on another article, Bruce. It's entitled, "Can CMP Surveys Help the AGN Community?" AGN is galactic centers?
Yes. Quasars are an example. The general class is called active galactic nuclei. And basically what's going on is that matter is falling into the central black hole in these galaxies. That causes energetic emission of radio waves and light waves and so on. The purpose here is to point out to the community that's interested in these things, look, Planck has just surveyed the entire sky. Many times at reasonable sensitivity, we've detected thousands of these accreting black hole active galactic nuclei. Please use our data. So that was the point of that little paper.
So see, these quasars, I remember a long time ago, Bruce, I haven't really studied this. They have this jets coming out of them, right? This very active jets that goes hundreds of millions of light years.
Yes, well, hundreds of millions.
Or maybe tens of millions.
Yeah, maybe tens of millions, but substantial distances. What's interesting is that the ones that Planck really sees best are the ones where that jet is pointing right at us. They're called BLAC objects, but they're aligned with us. And what's interesting is that they appear particularly bright because relativistic effects brighten the beam along the beam. So we're really seeing the effects of special relativity when we look at these guys. And because they're beamed right at us, if you think for a moment about a slight wiggle in the direction, the beam is narrow and pointed right at you, but the direction is flopping around a little bit, then it's not surprising that they're variable. And Planck has found that many of these sources do vary. Now, we knew that before, but Planck measurements made systematically, season after season, have proven this variability. And that's a nice set of observations for the people who are trying to make scientific explanations of these jets to improve their explanations.
So is it a paradox, or is it something that we can reasonably explain and Planck data sort of improves explanation, or an explanation doesn't exist today?
There's several explanations or theories about how these jets work, and Planck can help sort out which one fits the data best. I don't think there's any serious question that the jets exist because we see them both pointed at us and then pointed perpendicular to the line of sight. So they're sort of going across the sky. It's a well-studied and well-modeled phenomenon. But details of how the magnetic field interacts with a jet and things of that sort, Planck data may help with. Because we've got so many sources at so many frequencies at so many epochs, different times.
And these quasars, this supermassive black holes, really, but so they have to be feeding something for this to happen.
Yes,
right?
And that's why not all galaxies are active. Our own galaxy is not active in the sense of having material flowing rapidly into the central black hole. So it doesn't have one of these strong radio jets. Neither does Andromeda, but M87, another fairly nearby bright galaxy, does have an active nucleus.
Do we have any hypothesis as to the age of that I mean, do they sort of settle down after getting old? What's the hypothesis?
You mean like us? No, I think let me start over. It is probably the case that a higher fraction of galaxies were active in the past than they are now. So in that sense, yes, they settle down. But it's perfectly possible to have a galaxy as old as ours, or even older, still have an active nucleus. So statistically, yes, fewer now than in the past, but that doesn't mean that a particular galaxy can't suddenly start gobbling up stars and become active.
Yeah, so the point, the primary point of the paper is that there is data, there is Planck data that might help the AGN researchers to get better insights.
It's part of a general outreach by the Planck team to say, look, we've done a good job on cosmology, lots of papers published about that, but we also have done a good job on extragalactic radio sources and AGN. We have the best current high frequency maps of our own Milky Way galaxy. Come on, guys, use our data.
And who wouldn't? Who wouldn't want to use data, Bruce?
Say that again. Who uses it, or
who would not want data? I would imagine everybody would.
I think so.
That, right?
It's a question of not knowing about it. Remember, Planck was funded by the European Space Agency and NASA to do one job, and that is to measure these fluctuations as well as they can be measured, and secondarily to look for polarization. Everything else is free and gravy. Lists of sources, maps of the galaxy, things of that sort. But because it wasn't the primary aim, it's not as well known. So we've been trying to get the galactic scientists to pay more attention to our maps and the AGN community to look more carefully at our catalogs and so on. And they are.
Yeah, yeah. So in conclusion, Bruce, if you look forward 5 years, what would be the most exciting sort of finding, discovery, confirmation that might come
5 years,
for
5
you?
years is tough. If you gave me 10 years so that light bulb,
Let's take 10 years
I
then.
would
Yeah.
say clearly a much, much better upper limit on B mode polarized fluctuations or even a detection. That's the stuff of Nobel Prizes. In the meanwhile, we're going to be making better and better observations from ground-based instruments at very small angular scales. And my guess is that over the next 5 years, most of the progress in the field is going to be from those instruments, the Atacama's Cosmology Telescope, the South Pole Telescope, and the information extracted from those observations, which have not yet been published in full.
Right, right. Yeah, I mean, what's exciting about this is that you are getting data from different perspectives, ground-based satellites, different location, different sizes. So there is, opportunity for sort of meta modeling phenomenon now, right? Because this data, they are coming from different instruments, make it extremely
And that's
interesting.
right. I mean, look at the merger of the BICEP large angular scale data and the Planck observations enriched both experiments. And that's going to happen between Planck and the Atacama Cosmology Telescope, Planck and the South Pole Telescope. It's going to be ongoing. And lots of credit to very bright young theorists who are busy using these data sets, either singly or in combination, to extract more and more interesting things. We're getting close to the boundary of one paper per every microwave background photon. There yet, but we're working on it.
Yeah. I mean, that picture is, I would imagine it motivates, a lot of the young scientists and physicists to get to the field, right? Get
If
into
you
the
look at
field.
the standard picture of the microwave background that Planck has produced, you're seeing the universe as it
Yeah.
was 380,000 years after it began. You're seeing it in exquisite precision. You're seeing fluctuations that are at the order of a microkelvin or so in amplitude in some cases, against a background of 3 Kelvin. It's an engineering and scientific marvel. And yes, it does excite young people.
Yeah. Excellent. Bruce, this has been great. Thanks so much for
You're
spending
very
time
welcome.
with me. Yeah, and good
Thank
luck with
you.
this research.
Thank you very much. So long.
Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.